All right, everyone. Hello again. Let's keep talking. I am going to do some stuff predominantly for the Physics 209 course that I'm teaching. It's calculus based from the Katz book regarding physics. The Katz book, first edition. It's going to be chapter 19. We're going to be covering thermodynamics again. I've already lectured on thermodynamics. There's a number of ways things can be looked at, and my preference is always within the context of problems to talk about the content. Being able to solve the problems means that you know the content. So within the context of problems it's I think a great way to do a lecture. So the lecture I'd done prior to this hit some relatively major topics, hopefully decently enough that at least it puts us on the path to where we want to go. Now we do some of these problems from chapters 19, 20, and 21 from the Katz book, first edition. Hopefully that solidifies things quite a bit. That's the goal. That's the goal. So for chapter 19, I've got these 7 problems right here I'd like to do. And let's take a look at it. There they are from chapter 19. Problem number 6. They are saying hypothermia occurs when the human body temperature falls below 35 degrees Celsius. And hyperpyraxia occurs when the human body exceeds when the human body temperature exceeds 41.5 degrees Celsius. What are the equivalent temperatures on A, the Fahrenheit scale, and B, the Kelvin scale? I think what is really striking here is how fragile we all are, in a sense. How fragile the human body is. How strong it is and how fragile it is at the same time, I guess you'd say. The fragility of it is, you can kind of look at this just as a point of interest. Anybody looking to go into the medical profession and look at some of this stuff. Hypothermia, hypothermia. Hypo means under. Thermos is temperature. Has an association with heat as well. Don't know the language that good. I speak it at some level, but I don't know it that well. I'll tell you all the subtleties of it. But thermia, thermocracia means temperature. So thermos pertains to temperature, pertains to heat. Hypo is under, below. So hypothermia means the temperature of the human body went below what it should be at, perhaps substantially. That occurs when the human body temperature in Celsius falls below 35 degrees Celsius. And hyperpyraxia in Greek, hyper is the Greek equivalent to the Latin word super, above, meaning above. Hyper means above. You're hyperactive. I went to the doctor. I received a shot with a hypodermic needle. It went under my skin. Hyper. Hyperpyraxia. Pyr means fire. So it pertains to heat. So there's hypothermia. The temperature falls below where it should be. And there's hyperpyraxia, where the temperature goes above what it should be. Notice that 35 degrees Celsius and 41.5 degrees Celsius are not a great distance apart from one another on the temperature scale. That's 6.5 degrees Celsius. And look at it. With that, it gives you an idea, how much we depend on the climate, and for it to be reasonable, and how, how fragile the human body is. Look at this. I mean, there's only 6.1 degrees Celsius of difference for those two extremes, each of which is very dangerous. So, with that in mind, I mean, there's some things you can kind of note and deal with. Some are more significant than others, but you can look at, for problem number 6, the conversion to get a Fahrenheit temperature, and if they gave you a Celsius temperature, Fahrenheit temperature, if they give you a Celsius temperature, you can use this equation. So you get a Fahrenheit temperature if they give you a Celsius temperature. To get a Celsius temperature, if they give you the Fahrenheit temperature, you're talking about this. For hypothermia, we basically are looking at where would that be? Where would, the temperature in Fahrenheit would be 9/5 times the temperature in Celsius plus 32. I've already, we've already discussed that. Definitely can use that. So I think we're good that way. So got that. Well, what's going on? Well, 5 goes into here 7 times. 5 goes into here 7 times. 7 times 9 is 63. 63 plus 32 is 95. 95 degrees Fahrenheit. A person starts to get in danger of hypothermia, surprisingly, if their body temperature goes below that. Wow, doesn't take much, does it? Like we were just saying. Still staying with A there, guys. You've got T sub F, and here we go. You go 9/5, and they're saying that they're giving you this. It's a lot. It's a high temperature. Still a lot. It's definitely a lot. There's no two ways about it. In the Fahrenheit scale, there's a little bit more, a little more breath in the whole thing. But you're talking about, so it's about an 11 to 12, 11.7 to 12 or so, or whatever, close to about 12 degree window where there's two extremes that can happen. This is a horrible, horrible place to be. This is very, very bad place to be. Both of them are actually. When that does happen, there was some. It was mentioned one time on television. Experts were talking about it. I guess you could say heat-related illness. Heat-related illness causes more deaths in the world than any other of the phenomena of the climatological phenomena that occur. I think even combined, for sure, more than any of them. That's something else. So the heat is nothing to play with, nor is the cold for that matter. Extreme weather. It doesn't take a lot. There's a lot, not a lot of resilience. There's tremendous resiliency in humanity and the human body, but also there are pretty narrow windows of health and not health. So again, great caution is needed there. All right, that's 6. Anybody going to the medical profession, obviously you'll know that. They'll tell you that as well. For B, same kind of phenomenon here. They just, for hypothermia, and then so you got now let's do it with the Kelvin scale and see where it's going to go, and then he better. Hyperpyrexia. Overheated is what it means. Pyr is fire, so it's associated with, right there, right here. Pyr, fire, hyper, above, so very dangerous. Hypothermia, below where it should be. So hypo, below, hyper, above. So when you look at something like this, how are you going to do this in the Kelvin scale? basically all you got to do is take whatever you got in the Celsius scale and add 273. You see different numbers written in different literature. They use 273. This book uses 273.15. Doesn't really matter. For both of these phenomena, you're using this to get there. So if that's the case, if you take, for hypothermia, if you take 35 degrees, the Kelvin temperature scale and the Celsius temperature scale are, as far as the size of what they are, as far as the gradation, let's put it this way, the distance, the amount of temperature increase from 20 degrees Celsius to 21 degrees Celsius is 1 degree Celsius. The amount of temperature increase from 293.15 Kelvin to 294.15 Kelvin is 1 Kelvin gradation, 1 Kelvin degree. They don't use degree, they just call it Kelvin. 1 Kelvin rise in temperature is the same as 1 degree Celsius rise in temperature. So 1 degree Celsius and 1 degree Kelvin, as far as differences are concerned, as far as like the size of a distance, a traveling of 1 degree in rising temperature, or a traveling of 1 Kelvin in rising temperature, that 1 degree climb and that 1 Kelvin climb are identical. They're just separated by 273.15 on the ladder scale. One's on a lower, one's higher up than the other as far as the numbers are concerned. So make a long story short, whatever you got in Celsius, add this and you'll have Kelvin. It's that simple. Take 35 and add 273.15. You should get 308.15 Kelvin. So this is, in the Kelvin scale, this is 308.15 Kelvin for hypothermia, to be on the threshold of hypothermia. Same phenomenon here. You're going to put 41.5 right here for a temperature scale to be able to get there. And that one right there is going to get you 314.65. .65 Kelvin. So there you go. That's it. I mean, we talked about it, guys, and again, it's you got to emphasize and look at the window again, how that all plays out. See what we had here. I told you it wasn't a big window. It was like 6 point. We actually looked at the temperature scale, the 35 degrees Celsius and the 41.5 degrees Celsius, 6.5 degree Celsius, 6.5 degree Celsius temperature scale difference between the two. 6.5 difference between them. Well, if you take this and subtract that, it's 6.5 Kelvin. 6.5 Kelvin difference is identical to 6.5 degrees Celsius difference. Just kind of emphasis on that again. All right, that's problem number 6. Let's go to 17. Okay, guys, let me just get a different pair of glasses for a second here. Because if I look down, I see myself losing them, having them fall. All right, for 17, you guys. 17 at 22.0 degrees Celsius, the radius of an aluminum sphere is 7.0 centimeters. A, at what temperature will the volume of the sphere have increased by 3%? B, what is the increase in the sphere's radius if it is heated to 250 degrees Celsius? Assume alpha, the expansion coefficient, is, for linear, is 22.2 times 10 to the negative 6 inverse kelvins, and beta is 66.6 times 10 to the negative 6 inverse kelvins. So that's 17. Let's write a couple things down there, kind of keep a few things in our mind, and let's figure out where we want to go on that. All right, guys, kind of a significant thing here. If you look at how, volume changes, there's some approximations that go on. I'm sort of debating, sort of going there. If I do, it won't be for a very long duration vis-a-vis this problem, but they're talking about expansion and how stuff happens during expansion. It might be worthwhile taking a shot at it. Now, I'm doing this kind of cold, guys. Don't have it in the actual notes here, but I think it might be worthwhile saying this, what I'm about to say. Well, they got this thing. They say, what's this coefficient that kind of describes, there's a basic premise of what goes on here, guys. If you increase the temperature that some object is experiencing, it tends to expand, period. So the radius in this sphere should expand in a linear sense. A volume tends to expand 3 times. So there's a coefficient of linear expansion. And let me kind of write a couple things down here, guys, and we'll see how you guys feel about it, I guess. This coefficient of linear expansion, alpha, it just means if you take the initial length of something and you increase the temperature, then the more increase in temperature, the more expansion is going to occur. There's going to be a delta L. There's also a delta V, and there's a different coefficient, and it's beta, and that's V0, volume, and then delta T. Now look, if the temperature falls, it's going to contract. The volume will, the steel beam will, whatever. If there's enough of a temperature drop, there's going to be some level of contraction that's going to happen. If there's going to be a temperature increase, there's going to be some level of increase in length of the steel beam, for example. Okay. So you look at this, we know this. And they make a rather interesting claim. They say which one's which, in a sense, but let me, let's kind of go right here. Delta V divided by V0 is equal to beta delta T. True. So, I'll tell you what, keep going. Why don't you, you did that. Why don't you divide by beta as well? And what you get is you get delta T. Delta T is going to be delta V over V0 times 1 over beta. So that was just me manipulating this one right here. And then I ended up getting this. So you got this. Okay, great. Let's sort of back up a little bit on this. They said two things that I thought were of interest. They kind of said it in somewhat of a backhanded way, but they said that alpha was 22.2 times 10 to the negative 6 inverse kelvins, and beta is 66.6 times 10 to the negative 6 inverse kelvins. I'm not saying anything incredibly profound here, guys, when I tell you that. Well, let me just write it down, and you'll kind of maybe can visualize it all the more easier. This is inverse Kelvin, the coefficient to make it happen. There's no unit beyond that because you're multiplying it with meters, and you're going to get an increase in meters. This is for linear expansion. For volume expansion, it's 3 times more than that. It's 3 times more than that. Yeah, it's, it's a, I don't want to split too many hairs here, guys. The ratio's about 3 to 1. 3 times the linear expansion should tell you roughly, at least roughly, a very good approximation in many instances at least. 3 times the linear should tell you what the volume expansion coefficient is. Beta equals 3 alpha. Is that exact? It's very, very, at the least, it's a very, very good estimate very often. Not necessarily have to be at least, but it's a good approximation. Beta equals 3 alpha. Guess one way you could kind of look at that was, let's say I talked about a box. Let's talk about a box that had, let's say it was a cube. Again, I can't draw to save my life, but okay, let's something like this, right? The volume is L cubed. Yeah, fair enough. Fair enough. What if you heated it and it expanded in all 3 directions? Like, what do you mean? Well, I mean, this is what it is before I did what I just did. And let's say it's, it's expanded a little bit, guys. I don't want to, this is obviously a bit exaggerated. It's a lot bigger than the other one was. Let's just not worry about that. Let's just say, well, how does something expand? Well, there's going to be a delta L right here. The delta L is alpha L0 delta T. So you've got L plus, let me just leave it as delta L, it's a little easier to write. L plus delta L, L plus delta L. This all happened because of a temperature increase. It could have been a temperature decrease, guys, in which case this thing's going to shrink. In which case it's going to shrink. But I got this. Now what the heck's going on? Well, it gets a little, it might get a little messy, but the volume here is going to be the length cubed again, but be careful, it's going to be this. If you use the multinomial theorem, or at least a special case of the multinomial theorem, known as the binomial theorem, you can actually find out all the coefficients of what goes on with this thing when you actually do it. When you do this, you're going to find this guy to be L cubed. Wow, that looks familiar. L cubed. I got L cubed over here too. All right, and let's see here. Now we go. I think it comes out to 3. Again, there's a number of ways this can play, so let's play it all the ways we're going to play it. It's going to be this plus 3 L delta L squared plus delta L cubed, something like that. Now again, I told you, did not initially plan to go this way. It wasn't really in my notes, but so I'm trying to do this cold a little bit. I think it comes out that way. When you actually do something like that, if you were to take the quantity A plus B and cube it and use the binomial theorem, which is a special case of the multinomial theorem. Incredibly useful theorems. And that's completely analogous to what just happened here, guys. So, what they're trying to say here, guys, on something like this is, how would you look at it in terms of volume initial, and how that goes, the change in volume. If that's 3 alpha V delta T 0, the way that would actually play, let me just see exactly how we would do that. You're saying something like this, and the argument that they make is that delta L is really small. And if something really small gets squared, it's still really small. And if it's less than 1 and it's really small, and it gets squared, it gets really, really small. So this approaches 0. Something really, really small, and if it's less than 1 and really, really small, when you cube something less than 1, which is really, and it's really, really small, it's less than 1, it's going to be very small. You square something that's less than 1, let's say, or just small, relatively speaking, and you square it, it's not, it more or less kind of goes there. This is kind of where the 3 is coming from. And so I'm just trying to say exactly where we would actually go with that to actually say something like that. DL, that's it. That'll do it. And that's kind of getting it. So I guess this is, I'm not sure how far-fetched you might find this, but I guess you got to look at this, man. These are some pretty small numbers. 10 to the negative, 10 to the negative 6, 10 to the negative 6. Man, you're not getting, if that's in here. That's the alpha. That's 10 to the negative 6. Something associated, something multiplied with 10 to the negative 6. L0 might be very long, but it's probably not in the order of 10 to the negative, probably not in the order of 10 to the 6th. It could be, but, but anyway, I mean, you may need to be more accurate in certain circumstances, but for a wide range of circumstances, the approximation is really good. I was really adamant about not saying that beta is exactly equal to 3 alpha all the time. It's probably very, very close much of the time, and that's good enough for much of what we do. And this right here, the fact that we kind of threw these out, kind of tells you you're already doing an approximation. Now hold on, this is pretty important stuff. This 3L squared DL, let's put it up here. This, I always want to leave a lot of room for you guys to be able to see stuff. Let me go under here, I guess. This guy right here is the change in this is volume, this is going to be change in volume. Are you sure about that? Yeah, I am. This is square units, this is linear units, this is to the 1 power, this is to the 2 power. Linear units times square units is volume units. This is going to be the change in volume. Now wait a minute, this is still a far fetch away from what I was saying. For now it is, but it won't be for long. True. What is always want to leave myself enough room, guys. I want you guys to be able to see this stuff. What is delta L? Delta L is alpha L0 delta T. Oh yeah, L0 is the original length. Remember this should have been, forgive me after the fact here, guys. L is L, this is just the initial length. So this is the same as, you just easily could have started it with L0, This is the initial before something happened. If that's the case, again, that's the initial, that's the initial. Forgive me, you could have left the L in there and just known that it's the initial. If that's the initial, then we're definitely talking about this. That's fine, no big deal. That's this. Delta L is alpha L0 delta T, which is equal to, well, what is L0 times L0 squared? 3L0 cubed. L0 squared times L is L0 cubed. L0 squared times L0 is L0 cubed. Here's alpha. Here's delta T. Okay, let's see what we can say here. We've got these. We've got them in the book. You have it written down here. So we know all this. Let's just see what we can say. If there's anything useful here for us. What is going on here? Well, I'll tell you what's going on. You got 3 alpha in front. We got delta V. Just put the alpha right next to the 3. L0 cubed delta T. Wait a minute, ladies and gentlemen. Isn't the original V, the original volume, L0 cubed? The original volume is L0 cubed. Didn't we say that beta was at least approximately equal to 3 alpha? This is the original volume, you guys. I mean, I don't know. Maybe, I hate to be doing this as we go along. I mean, the initial volume is V0. Forgive the use of the, as we have the subscript there, you guys, the language we can use can be a bit confusing, but we understand. Initially, we're talking about an initial situation. What is that? Well, the L is equal to L sub 0. The V is equal to V sub 0. And what happens at the end? There's going to be a V. There's an L, too, but we're not really going in that direction. So I just put L sub 0s there. Well, that pretty much solves the problem, guys, is what it does. This is where this is essentially 3 alpha right here. There's your beta. This is V0. This is delta T. Yeah, we knew that. Now you might say, that's great, Malus. You kind of use something that's kind of easy to deal with. It's called a cube. Yeah, I did. You know what? I can use that thing that's relatively easy to deal with. I can use that thing called the cube. I can use it on any volume. When I'm in 3-dimensional space, I can use that any volume. A sphere? Better believe it. I could put a whole bunch of cubes inside that sphere and approximate how big that sphere is. If you don't like that approximation, I'll make those cubes smaller. If you still don't like it, I'll keep making those cubes smaller. And what happens to each one of those cubes? When they are heated up, for example, all those cubes that if I keep making them smaller and smaller and smaller, you're not going to be able to differentiate what the sphere is or what the conglomeration, this almost infinite number of tiny cubes are. Won't be able to tell the difference. If it's still not a good approximation for you, we'll keep making it smaller and smaller. We'll do all the calculus that we need to do to get it done. What's the point, though? The point is this. We can do it. It's a good approximation. Every one of those cubes is going to behave like what you just saw. Every one of those cubes is going to have this happen. The difference is that every one of those cubes is going to be really tiny. Each one's going to have a volume of V0, but it ain't going to be as big as this V0 was. It's going to be tiny, tiny, tiny. Fine. If you add up all those V0s, how do you do that? You multiply by the number of cubes. If you multiply all those if you put all those V0s together, because each one of these is going to change the volume just a little bit. And if you take all of them as they're changing the volume, you're going to get the final volume. So basically, if you were taking, for that right there, if you added, and I mean really added, I mean it's just something out of control added. But this right here, if you added them all together, again, I don't like erasing any of this, but you guys got it on film, so. You guys got it on film. Let's take a look at it. The real big delta V is going to be, the real big one is going to be beta times V0 small, really small, V0, let's say, I don't know, 1. Put a little 1 there. I don't know how well you can see this, guys. I'm trying to kind of, V01 delta T plus beta V02, and these are tiny cubes, guys, plus dot, plus V0, and I mean Vn, this could be an n right here, that could be a million, that could be a billion. You still got a problem with a billion? Let's make it a trillion. We can go on forever. We got this. Okay, so what? What's the big deal? Well, wait a minute, temperature's temperature. They're all experiencing the same temperature. Put beta, why don't you factor a V0, why don't you factor the V01, the V02, and in fact factor all of them out of there, all of these V's out of there. Factor all of them out of there. You got this, V0, you got delta T. Looks good, it almost looks too easy. I just want to make sure I didn't do anything careless here. Yeah, this is fine. This is fine. These three items, beta, V0, and delta T. I've got a question for everybody. Don't know how good that looks, guys. Let me see it. You can see it. I hope you can see it okay. If not, I'll just put this under here too. What is that? That's the volume of the whole thing. That's all those little cubes give you the sphere. They give you the sphere. They give you the cylinder. They give you the pyramid. They give you the cone. They give you that incredibly amorphous mass of steel that's there that I can't put any sort of label on it, but it's there. I can put an infinite amount of cubes, or close to an infinite amount of cubes, tiny cubes, to kind of mimic what's going on in that huge amorphous piece of steel out there, how it's going to expand. How it expands? It's going to expand the same way as though it were a block of steel that was a cube. As far as like its change in volume. You add these together, you got V0 delta T. Pretty important stuff. Pretty important stuff for this particular aspect of thermodynamics when we talk about something like this. Okay? All right, well, I guess in all that excitement, I guess we got to answer the question that was asked of us. I think this is going to get us there, at least initially, for some of what we're doing. Let me get rid of some of this stuff up here, guys. Interesting stuff. And you remember in the lecture on thermodynamics in general that I tried to give, and I don't think any of the great mathematicians or physicists have anything to worry about regarding my presentation of something, but you saw that we tried to talk about what would happen if the container that contained the gas and all the items were moving around? What if that container wasn't something easy to look at? What if it wasn't a cube, a cubic box? What if it was a cylinder? What if it was a sphere? And we said we could, or some kind of amorphous solid structure that had the gas in there. How can we do the derivations? Again, if we're careful, we can break stuff up into small, well-behaved volumes and then talk about how the pressures are associated with that. If you remember, I talked about that a little bit. At least a little bit I brought that up. Well, it's kind of going in that direction here. Again, the small volumes can get us there. Whether you're talking about trying to figure out pressure in an amorphous three-dimensional container, it's not a very good, it's not a container that, hey man, I can't, it's not a sphere, it's not a cube, it's not a cone. I mean, not that a cone's an easy thing to look at either, to be honest with, right? But it's certainly, it's not, the easiest one is the cube. If it's not a cube and if it's anything else, can you actually find pressures? Can you actually talk about some of the theory? Sure. If you break things up, there are a lot of interesting mathematical ploys where you can break things up into well-behaved volumes and discuss that matter regarding pressure, regarding some thermodynamic aspects that are very important, very useful. The same thing is happening here. You're breaking it up, whatever it may be, into well-behaved volumes. The most well-behaved volume, as far as I'm concerned, is the cube. L times L times L, L cubed. L sub 0 times L sub 0 times L sub 0. L sub 0 cubed, that's the volume of the cube. It's the easiest one to look at, okay? Well, like I said, all that excitement, you guys, we're talking about at 22 degrees Celsius, the radius of a solid aluminum sphere is 7.0 centimeters. A, at what temperature will the volume of the sphere have increased by 3%? B, what is the increase in the sphere's radius if it is heated to 250 degrees Celsius? And they said assume alpha is 22.2 times 10 to the negative 6 inverse Kelvin, and beta is 3 times that. And we already explained why it's 3 times that, or close to 3 times that. Beta is 66.6 times 10 to the negative 6 inverse Kelvins. Okay, so let's leave a few things up there. Let's take a few other things off, and I think we're okay. All right, so well, I'm going to come right over here, and that's going to get me there. I want to get the percentage. They're talking about the volume changing by 3%. The volume changing by 3% means delta V over V0 is equivalent to 3%. Well, delta V over V0 being equivalent to 3% is 3% is equal to 0.03. So if this guy is 0.3%, I'm sorry, if that's 3%, then 0.03 is what 3% is equal to, and then 1 over beta, and that will tell me what the delta T is. Let's go for it. Take this and come over here. So let's see what we got here. Delta T equals delta V over V0, which is 0.03. It's a 3% 3% change in relation to the original, 3% change in volume in relation to the original. What does that mean? Delta V over V0 is what that means. 1 over beta. Just said beta was this. Okay. Go for it. You almost think it's going to be something huge because, I mean, that's, you know, but you got this dividing into there, and that's a small number, so maybe this comes out okay. At the end of the day, you guys, the delta T is 450.45 degrees Kelvin or degrees Celsius. Doesn't matter. We're talking about a change here. The change. That's how much would happen. That's a big change in Celsius temperature for a change of 0.03. For a change of just 0.03. And that's where they're coming from regarding that. So when they're saying for 17A, at what temperature would that be? I'm just going to take, it was at 22 degrees Celsius. I'm adding 450.45 degrees Celsius. What would the new temperature be in terms of Celsius temperature? Yeah, absolutely. B, they're saying, you know, stuff's easier. What is the increase in the sphere's radius? Assume this. Well, look, this gets a little, can potentially get a little messy, but I don't think it will. The radius of the sphere is a linear parameter, so to speak. It's a linear phenomenon. It has ramifications, of course, into the volume of into the reality of the volume of the sphere changing. Make a long story short, it's proportional to the cube of the radius. Okay, interesting. But right now, I just want to talk about the radius itself. Can I kind of keep this in mind and maybe get away with the whole thing? Here's alpha. Here's L0 delta T. Here's delta R. Forgive me here. That's alpha. It's not 66.6. It's 22.2 times 10 to the negative 6. They're both 10 to the negative 6. 7 centimeters, I guess you can leave it. They're not. There's no unit here for length. It always goes with the units that you've given it. It's inverse Kelvin. There's no inverse meters on there or anything like that. Or inverse centimeters or something. It just goes with whatever you have. You have changed it. You're going to go up to 250 Celsius. You started at 22. Grind that out and you should be done. Delta R, and let's just see here. Right, delta R is going to be that whole song and dance right there, you guys. So 0.03543 centimeters. Yeah, if this was miles, it'd be in miles. If it was meters, it'd be in meters. If it was kilometers, it'd be in kilometers. That's not a big deal. Here they kind of, you get off you're off the hook on this one when they say that. And that is it. That's it. Let's go to 33. Okay, guys. For 33, the ideal gas in a container. The ideal gas in a container is under a pressure of 20 atmospheres at a temperature of 27 degrees Celsius. If half of the gas is released from the container and the temperature is increased to 50 degrees Celsius, what is the final pressure of the gas? Okay. This thing about atmospheres ain't a big deal. I mean, we can convert atmospheres to a lot of things. I mean, to a number of things. Usually it's pascals. Every 1 atmosphere is equal to 1.013 times 10 to the 5th pascals. So I can convert between pascals and atmospheres if 1 atmosphere is equal to 1.013 times 10 to the 5th pascals. I can convert between the two of them, pascals and atmospheres. It's not a big deal there because it's got sort of an absolute character to them. I can go all the way down to no pressure, which is 0 pascals, and that corresponds to 0 atmospheres. Or I can go up, and it's sort of it's a linear scale, and there's an absolute 0 there. There's not an absolute 0 in the Celsius temperature scale. Everything is geared to an absolute temperature scale. As I've already said, you could almost make up your own temperature scale as long as there was an absolute 0 in it. You could make the physics work. Otherwise, you're not going to be able to solve the physics problems. You have to have an absolute 0 temperature scale. The absolute temperature scale that we use is the Kelvin temperature scale, and therefore these temperatures have to be converted from Celsius to Kelvin. Okay. After that, it's not that bad at all. 33, again, there's things I have said and things that you have read. So let's repeat some of them. We know that's true. We know that's identical to this. The mathematics holds only for absolute type temperature scales. We've already said that. The mathematics holds only for absolute type temperature scales. If that's the case, there's a number of ways to go. Let's probably work with, theoretically, you could actually work with either one, to be honest with you. Because half the gas being released goes from N to 1 over, half the gas being released goes from N to 1 over 2 times N, or N divided by 2. So it's not a big deal. Either one works. I'll use the top one on this one. There is a final situation involving pressure, involving volume, involving number of particles present at the end of all that. KB is a constant. That doesn't change. There is an absolute value temperature, finally, of T sub F. There is initially it's this. All right. Okay, guys, for some reason, I'm trying to... Could have sworn I had more chalk, guys, but okay, I got enough, so let's see what we got. What's going on here? Well, I don't know. To me, so much pertains to ratios. Those who have had me as a teacher up close in a face-to-face lecture format know that I'm really big with the idea of ratios, how things relate in terms of ratios. It's not just that I'm really big about that. I think all of mathematics is big about that because that's the way it works. You've got to be talking about ratios when you're comparing how quantities interact, how they change. One quantity changes by this much, by how much will another quantity change, so on and so forth, right? Ratios play a huge role. Let's make a long story short. K sub B and K sub B cancel out. What else? Well, I'll tell you what. They told us with the container, I don't think they did anything crazy with the container. They left the container alone. The ideal gas in a container is under a pressure of 20 atmospheres at a temperature of 27 degrees Celsius. If half of the gas is released from the container and the temperature is increased by 50 degrees Celsius, not to 50 degrees Celsius, by 50 degrees Celsius. So it went from 27 degrees Celsius increased by 50 is 77 degrees Celsius. So from 27 degrees Celsius to 77 degrees Celsius, what is the final pressure of the gas? Ladies and gentlemen, they did not change the volume of the container. So what we have here is there's a final pressure that they're asking for. There's a final pressure that they're asking for. And I'm going to tell you what, the final volume is the same as the initial volume. And we'll cross that bridge as we need to cross it. They also told us half of the particles were released. This guy right here, NF, is 1/2 what the initial situation was, 1/2 Ni. True. The temperature was increased. Now, it went from 27. It went from 27 degrees Celsius to being increased by 50 degrees Celsius, which means it went from 27 degrees Celsius to 77 degrees Celsius. You can't use those numbers for ratios. You got to go for an absolute temperature scale or you're lost. 27 degrees Celsius is 300 Kelvin. Um, 77 degrees Kelvin is 77 degrees increase in Kelvin temperature is 50 degrees Celsius increase in temperature is the same as 50 degrees Kelvin increase in temperature. 50 degrees higher, it's this. They are telling us, don't worry about this so much. In fact, they might want, depending on, they'll usually tell you how they want the answer. They're saying 20 atmospheres, right here. I'm not going to play too many games with that. I'm going to let it be. I'm going to let it be. There's a lot going on here, guys. VI and VI cancel. NI and NI cancel. You've got PF over 20 atmospheres. I'll just say 20. We know it's atmospheres. I'm going to give the answer in atmospheres, and I can do a lot of stuff after that. These cancel. You got a half. How do you want to do this? There's a lot of ways to go here. Half of this is 175. This is 300. The rest is cross multiplication, you guys. You can cancel stuff out. You can do a lot of stuff. The rest is cross multiplication and solving it. I mean, you can do a whole bunch of things here. I'll tell you what. 25 goes into here 7 times. 25 goes into here 12 times. You don't have to do what I'm doing. You could start doing this thing. 7 times 25. 12 times 25. It's just atmospheres. As long as you're consistent, you're okay. Because there's an absolute temperature, there's an absolute scale. There is a 0 for atmospheres. There is a 0 for pascals. If they were somehow on a different scale that was, staggered the way the Celsius and Kelvin temperatures are staggered, that would be an issue. It's not though. Here it's not. Cross multiply, guys. So you got this, you got that. 12 PF equals 140. PF is equal to 140 over 12. If this was 144, you guys, 144 divided by 12 is 12. It's 4 short of that. 4 short of that is going to be an answer which is 4 over 12 less than 12. 4 over 12 is a third. It's going to be 11 and 2/3. 11 and 2/3 atmospheres. Atmosphere. Yeah, it's roughly 11.67. If you're going to convert this stuff, again, they usually don't like writing things as mixed numbers. They want easier manipulation is going to happen if you make them into decimals. It's approximately this many atmospheres. If you multiply 11.67 atmospheres by 1.013 times 10 to the 5th pascals, you get 1.182 and there it is. At the end of the day, there's your answer, guys, with this thing. Again, because atmospheres are on a scale that's got an absolute zero. It's not temperature, but there's an absolute zero. There is a place where you're not going to go any further. As far as there not being, I don't want to get into too many mathematical arguments here. For our purposes, there's no pressure. That's as low as it's going to go for that. So the way the scales are, you can use pascals or atmospheres, but you have to be consistent. Temperature, you have to have an absolute value type of temperature for this to work. So that's 33, you guys. Let's go to 34. Dexter has developed a special knockout gas that is kept in a 0.0650 meter cubed cylinder at a temperature of 17.25 degrees Celsius. If the container is holding 10 moles of gas, what is the gas pressure? The container is holding 10 moles of gas, what is the gas pressure? That's A. B, if the radius of the top of the cylinder is 0.30 meters, what is the force the gas exerts on the top of the cylinder? Pretty basic stuff, guys, but very useful. So let's see what we're going to say there on that, what he does. We're going to put a few things down, and I think we're going to be in good shape. Okay. I'm sorry, for 30. Pretty straightforward stuff. For 34, you guys. So let's see what we say. He talked about that knockout gas and the whole thing here and what's going on. Pretty straightforward. What it's going to be is you're going to, some big time bread and butter here, you guys. This we've talked about ad nauseum, and I think it's pretty important for us to have done so. So there it is. And then we say how pressure relates, how it all plays out. You got this. Then they're saying, okay, then go ahead. Tell me what the pressure is, given what this gentleman is talking about. What's going on here? What are they trying to say? He says he's got 10 moles. 10 moles there. We know that 8.315 is the constant. We also know that the gas is at 17.25 Celsius, but that doesn't help me unless I'm converting that to an absolute type temperature scale. Let's use the one that's really famous called the absolute value, the Kelvin scale, right? It's got to be Kelvin scale. Otherwise, if it's not, it could work, but you'd have to change the constant here from something else, some other scale. See exactly what you would say. Yeah, you'd have to. You can change constants all over the place, guys. You can change measuring sticks, but when you're doing a comparison, I can't compare a 100-degree Fahrenheit day to a 50-degree Fahrenheit day by saying, hey, 100 degrees Fahrenheit divided by 50 degrees Fahrenheit. Degrees Fahrenheit cancel. 100 over 50 is 2-to-1 ratio. There's not 2 times the average kinetic energy associated with the molecules in the air. There's not 2 times the average kinetic energy as there is in a 100-degree day as there is in a 50-degree day if it's Fahrenheit temperature scale. But if that was Kelvin, and let's say there was a gas and it didn't liquefy, didn't whatever, say, yeah, it's flying around. Yeah, 100 degrees Kelvin compared to 50 degrees Kelvin, the ratio of 100 divided by 50, 2-to-1, on average, the 100 Kelvin gas, that's still a gas, moving around, let's say it's all a gas, let's make it a mathematical model, let's say it's possible to do something like this, and there's the 50 Kelvin gas, the 100 Kelvin gas has double the kinetic energy per molecule on average than the 50 Kelvin gas does, for sure. That's if you got to have the absolute value temperature. So you got to have things go absolute value temperature if you're doing this comparison, you guys. You don't do it, you're going to have problems. It's not going to work. They're talking about, I think they talked about cubic meters. That's all right. That's good. It's all there. If that's the case, you guys, that punches out the answer for us. 3.715. That's that. Okay, absolutely. That's that. Now what about the force? Well, okay. Isn't pressure force over area? Therefore, P times A will give me the force. True. If it's a cylinder, there is a circle, top and bottom. I mean, if you're having it, right side up, so to speak, if you don't have it sideways, let's say, the circle's on top, we're assuming circle on top, circle on the bottom, okay? If you stand it up that way, if you're going to just stand it. Yeah, that's all it is, guys. So at this point, we got the pressure of 3.715 times 10 to the 5th times pi times, I think they told us that the radius, I'll check on this, was 0.3. Make sure that wasn't a diameter. If that was a diameter, you'd have to divide it by 2, and the 0.3 would be 0.15. They are saying that the radius of the top of the cylinder, assuming that's a circle on the top of the cylinder, obviously, the radius of the top of the cylinder is 0.30 meters. What is the force the gas exerts on the top of the cylinder? 0.30 meters is the radius of the top of the cylinder. So that's it. You just grind that out, you guys. It started here. We know that pressure is force divided by area. Pressure is force divided by area. If you multiply by area on each side, you're right here. And that's the hardest part of the whole problem, you guys. The rest, you're grinding this out to make it happen. So what do we got here for B? So pretty remarkable. I mean, according to this, I mean, it's what it is. I mean, you wouldn't, I guess at first glance, given what you're being told, you're not thinking it's going to be something like this, and yet it is. So that'll be it. Yeah, absolutely on that one. Okay. It's 34. Let's go to 44. Now 44, I have a packet of stuff here for you guys. And I don't have 44 in that packet, but I have it in another packet where I'm talking about the ideal gas law and things of that nature. So, excuse me. All right, guys. So I do have 44. Again, it's in the ideal gas law discussion pertaining to such matters. Let's see what the heck that is. And I got some other stuff. So in the ideal gas law handout that I have for the people that are in my classes, and I have posted on Canvas, called Ideal Gas Law, and we proceed from there. It's looking like this. So there's 4 problems. Some of them are repeated in the stuff that I'm handing out, more like in the practice homework and stuff like that, and in discussion, lecture discussion. There may be there might be 1 or 2 that's not. For sure, 44 is not. It's from chapter 19 and chapter 21. So for chapter 19, number 44 is something I'd like to do now, and it's a little bit independent from other stuff I've given, but I think we're going to be fine to do so. Okay, let's go there. For 44, for 44, the gauge pressure of a truck tire is 2.72 atmospheres at 22 degrees Celsius. So let's start that. So problem number 44, again, chapter 19 in the Katz book, and there's a little bit of extra I'm doing here. Problem number 44, the gauge pressure of a truck tire is 2.72 atmospheres at 22 degrees Celsius. As the truck is laden with deliveries and driven around town, the temperature of its tires increases to 52 degrees Celsius. So it went from 22 degrees Celsius to 52 degrees Celsius, guys. What is the gauge pressure in the tire at 52 degrees Celsius if the volume of the tires is assumed not to change? Well, the volume of the tires we're assuming has not changed. Let's take a look. Let's see what they're giving, and let's go with it from there, you guys. It should be, again, pretty straightforward stuff when we're talking about this. fact, the most difficult aspect of this is me finding my erasers, right? I mean, so let's see what we got here, guys, for 44. All right, guys, put something new on this eraser right here. Maybe be a little easier to deal with. All right, guys, let's talk. I think it's really straightforward, so I think we're good. Let's play the game as we've been playing it, I guess. You're talking about, again, that classic equation that answers so much, explains very much. There is a final pressure, a final volume, an initial amount of moles, or a final amount of moles of something. R is a constant. T sub F, absolute value temperature, is something. P sub I, V sub I, Ni, R T sub I. Well, I mean, if this looks like something you've seen before, it should. I mean, it's again, this is kind of the bread and butter of a lot of what gets discussed. It's pretty straightforward stuff, too. And you saw me when we did some of this stuff we talked about how you can even derive these relationships, or at least explain these relationships in terms of the kinetic theory, in terms of just actual movement. The billiard balls are flying all over these tiny billiard balls are flying all over the place. What's going on? What's going on is we treat them like they are objects flying all over the place, making perfectly elastic collisions, and we can answer a whole lot. So we have what we have here, guys. We're looking at this. These two guys should get us where we need. I think if I'm going to do that ratio business again, I think I'm in business. It should be pretty straightforward. I mean, we note a couple things here. Look, nobody filled up or took out air from the tires. Nobody put more air into the tires, nor did they take out air from the tires. They've not put in nor taken out air from the tires. Small ni equals small nf. Capital Ni equals capital NF, the number of particles that are present. We also know that we're assuming that the volume of the tires didn't change substantially. And we, of course, know that R equals R. So that's not changing either. So those three things are up there. Tell you what, if that's the case, if you're going to take, there's a number of ways to do this. PF, VF, just divide the two equations like you did in the past. Divide the two equations. R is R, TF is TF, TI is TI. We know all that we need to know. We just said that VI equals VF. VF is the same as VI. NF is the same as NI. R is the same as R. PF over PI equals TF over TI. Okay. Now what? Again, there is an absolute scale, both in regard to pressure, so you can get away with a lot of it. There's a zero. There's a zero, and it's not going lower than that for our purposes. There are differences. What are you talking about? There's a negative pressure here. Yeah, but I can make it a positive pressure if I go the other way in terms of magnitude. That's neither here nor there right now, guys. The big thing is just know that this is all right. This is okay. So what you have here it's going to make the whole thing happen right here, guys. This is going to make the whole thing happen. So what happens is we need to be now here's where we got to be a little careful. This is true. This is the hard. I don't want to say it's the hardest part of the problem. It's probably the most important part of the problem. What I just wrote down there is the most important part of the problem. But they're saying there's a gauge pressure the gauge pressure of a truck tire is 2.72 atmospheres. That's a different dynamic. The gauge pressure, there's an absolute pressure, which is what I want, and there's a gauge pressure. And the gauge pressure is the difference between the atmospheric pressure and the absolute pressure. I'll make a long story short. Whatever the gauge reads, add this much, and you know, because the gauge is not going to bring in the atmospheric pressure, an atmospheric pressure worth of push out that's inside the tire, because the atmosphere is on the outside pushing back in. There's at least one atmosphere pushing out of pressure, but there's also 1 atmosphere. So there's 1 atmosphere of pressure. In all the pressure that's present, in the absolute pressure that is present, 1 atmosphere of that pressure is certainly trying to push out. Yeah, but it's equal and opposite to the 1 atmosphere of pressure given by the atmosphere right on it. So it doesn't measure when you put the gauge. The gauge gives you a reading which is 1 atmosphere pressure less than the absolute pressure. We need absolute pressure to put it right here. We need it for this guy right here. So whatever this guy is going to be, we want, that's the final here. The initial is also an absolute, it's gauge plus 1 atmosphere. So that's that's a pretty big thing. I mean, that's something you got to keep completely in the back of your mind to make this thing happen. Well, what does that mean? There's a number of ways you can do it. So, and I've got it written like that, you guys, for you. So I think you're going to be all right when you see it. I've got this and I've got that. And that's what all that is, and that's what all that is. Okay? So what they're trying to say is they want to know what the gauge pressure is. What's the gauge going to read for this one? Let's see here. What is the gauge pressure in there? So they're kind of playing some games with us here that we got to play with them. Let's figure out exactly how we want to do that. So the way I did it was I looked at it here and I went, okay, let's talk. Let's find the final absolute pressure, or kind of go in that direction by going PI times TF over TI. So you're going here. You got that's going to settle it. But to settle it, you got to be careful. The final absolute pressure, I don't know what it is. So let me leave it alone. Let me leave it alone for a bit. And I'm going to say, let's go for the final absolute, then I'm going to find the gauge. This is the guy I got to find. At the end of the day, this is what they're asking. That guy right there. When I get this guy, I subtract 1 atmosphere, and I end up getting that guy. So let me see. Let's just do that. That's where it's at. Now be extremely careful. It went from 22 degrees Celsius. It rose 30 degrees to 52 degrees Celsius. So if that's the case, you're talking about a situation where I'm going to say that, and I write it a little differently in my notes here, but I'm opting to go like this right now. Go PF right here, and that's going to be absolute pressure. That's going to be equal to the gauge pressure. That's going to be equal to PI. PI, ladies and gentlemen, is PGI plus 1 atmosphere. Initially, it's 2.72 atmospheres gauge pressure. If you add 1 atmosphere, 2.72 atmospheres plus 1 atmosphere is 3.72 absolute pressure. That's what I got to use. 3.72 atmospheres absolute pressure. Fantastic. Now, it was 22 degrees Celsius. What's 22 degrees Celsius plus 273? That's 295 Kelvin. That's 295 Kelvin. What is 273 Kelvin? And now, right? And so we did 22 degrees Celsius plus 273 Kelvin and got 295 Kelvin. Then we took 52 degrees Celsius and added that on to 273 Kelvin. That's going to be 325. That's it. Now remember, let's just do it again. You got to have an absolute temperature scale. 22 degrees Celsius plus 273 is 295. 52 degrees Celsius plus 273 is 325. It's as simple as that. This is the absolute pressure in the tires at the end of all that. So when you actually grind it out. So what we got is, it's a lot. It's a lot. It's more at least. We know that. It's 4.1 atmospheres. That's absolute pressure. Yeah, I don't want that. I want this. I want PGF. I want the gauge pressure final. If I subtract 1, that's PF minus 1 atmosphere. Well, PF is 4.1 minus 1 atmosphere. 4.1 minus 1. PGF, 4.1 atmospheres minus 1 atmosphere is 3.1 atmospheres. So you got two things here, guys. This is absolute. This is the absolute this is the absolute pressure, and this is the pressure above atmospheric pressure, which is absolute pressure minus 1 atmosphere pressure. So the 4.1 minus 1 atmosphere pressure will give you the gauge pressure. The gauge pressure is how much pressure is it above the atmospheric pressure that it's fighting. Well, 4.1 minus 1 is 3.1 atmospheres. That's the gauge pressure. So that's kind of where it's coming from, guys, when they're doing this stuff. Stuff is usually easier done than explained sometimes, as you can see. But you'll see it in the notes if you look at the discussion I give on the ideal gas law for this particular problem. And I'm posting all the other problems except for this one, but this one's here on tape. You see me talking about it. And you'll see it, like I said, Let me just see, make sure that was all that was asked. I think that was, yeah, that's it. And as we said, that's just in the ideal gas law handout that I have on Canvas. All right, so looking pretty good that way, you guys. So that's that, you guys. We got 53 and 81 to do, and that'll be it for that, okay? So okay, 53, ladies and gentlemen, 53 and 81. So let's look at 53. 53, an air bubble starts rising from the bottom of a lake. Its diameter is 3.60 millimeters at the bottom and 4.00 millimeters at the surface. So its diameter increases from 3.60 millimeters to 4.00 millimeters at the surface. So at the bottom, 3.60 millimeters is the diameter of the air bubble, and at the top, 4.00 millimeters at the surface. There's less pressure, so I guess the volume would be bigger. The depth of the lake is 2.50 meters, and the temperature at the surface is 40 degrees Celsius. What is the temperature at the bottom of the lake? Consider the atmospheric pressure to be 1.01 times 10 to the 5th pascals, and the density of water to be 1.00 times 10 to the 3rd kilograms per cubic meter. Model the air as an ideal gas, and model the bubble as being a container, a spherical container. Well, as we said, there's a diameter at the bottom, which is not as big as the diameter on top. On top, there's a higher temperature, so the gas will expand, so the container will essentially get larger, let's say, or it'll expand a bit. So the pressure should be different and everything else. So what are they saying here? What is the temperature at the bottom of the lake? For problem number 53, we're going to say this. So like I said, I read the question, and I also, while I was reading it, kind of said a whole bunch of stuff about it. So hopefully hopefully that's useful at some level. Let's see what we can say for number 53. Well, let's see. I mean, they're saying here, there's a lot going on here, guys. There's pressure associated to find the absolute pressure of what's going on here, guys. And like I said, you got an air bubble at the bottom of the lake. Its diameter increases as it rises. We want to find what the temperature at the bottom of the lake is as it rises through a distance h, let's say. Well, its diameter increases at the top of the lake. At the surface, it'll have a bigger diameter than it had at the bottom. The temperature at the top of the lake, we would assume, is larger than the temperature at the bottom of the lake. They're telling us a few things. Do we know enough to give the answer? Well, I'll tell you what. To look at pressure, we got to be looking at, notice how I solved that last equation, or that last problem. Problem number 44, how we looked at it. We really had to deal with absolute pressure. We couldn't playing with gauge pressure inside of the ideal gas equation is every bit as disastrous as playing with degrees Celsius in the ideal gas equation. You don't play with gauge pressure. You need absolute pressure, you need absolute temperature. It's as simple as that. What is the absolute pressure? The pressure at the bottom of the lake, or anywhere in the lake for that matter. Well, what's the pressure at the surface? At the surface, you're not under the lake. It's just the atmospheric pressure. The pressure at the surface is just the pressure of the atmosphere, pressure at the surface. The pressure at the bottom of the lake is equal to rho g h. We've been there, we've done that. Rho GH is the pressure at the bottom of the lake. It is the gauge pressure, so to speak, at the bottom of the lake. What's the absolute pressure at the bottom of the lake? Well, it's the weight of all the water, so to speak, plus the weight of the air that is above the water. It is the weight of all the water, so to speak, divided by area, plus the weight of all the air, so to speak, divided by the area again. So, what's going on, what the water is doing all by itself, plus what the air above the water is doing, is the pressure at the bottom of the lake. What's the pressure at the top of the lake? Well, that's at a depth h. The depth at the top of the lake is 0. So it's just that. Okay? You can essentially use, they're pretty clear on this. And then I write the wrong thing down. We write them both down, so it's not the wrong thing. You can use this. You can use this, or you can use this. All right, guys, we've been down this path in this short period of time quite a few times. So you can use one or the other, and you're going to be fine there. The ratios all behave themselves, if you allow me to say it like that. Let me use the letter S to mean surface. Let me use the letter B bottom of lake. Sounds good to me. Let's deal with it. The pressure. This is absolute pressure, guys. This is absolute pressure that we're dealing with. And if you want to talk about absolute pressure, yeah, that's a big thing. We talked about it, and that's it's going to play a role. Let's talk. Pressure at the bottom of the lake. The pressure at the bottom of the lake, volume of the bubble at the bottom of the lake. NKB T sub B. Surface. Notice I didn't really mess with the N, the capital N. It's the same amount of molecules in the bubble in both circumstances. Same amount of molecules in the bubble in both circumstances. K sub B is the same in both circumstances also. All right, the rest should be pretty straightforward for us, guys. PBVB Let's go. Same amount of molecules in the bubble in both instances. K sub B and K sub B are the same in both instances. Let's talk some more. The pressure at the bottom, ladies and gentlemen, is the weight at the bottom divided by area, which is rho GH at the bottom, plus atmospheric pressure. That's the pressure at the bottom. What's the pressure at the top? It's only atmospheric pressure. It's only atmospheric pressure at the top. So what's going on here? So at the top, at the bottom is P atmosphere plus rho GH. Pressure at the bottom is just P atmosphere. Let me just write this a little larger, guy. It should be pretty, I'm thinking it's legible, but let me just check. I think it's legible enough, guys. So this is P, this is in the notes as well. P atmosphere plus rho GH, you got this right here. The volume at the bottom volume at the surface is volume at the surface. We're talking about a sphere. We're talking about spheres, guys. All of this canceled. This has got to be absolute value temperature. 40 degrees Celsius on top, 40 degrees Celsius on top is 40 degrees plus 273, right? Which is 313. Let me take that back. It's yes, actually, no, let me not take it back. That should be 300, yeah, 313.15. All right, we'll figure out where it's going. All right, let's keep going. There it is. Here it is. Let's go. 4/3 and 4/3 cancel out. Pi and pi cancel out. Okay. We're doing a little bit better. We've got a whole bunch here. Oh, we can talk. Yeah, I mean, so let's see what we got. We got P atmosphere plus rho GH over P atmosphere. Times R sub B cubed times the ratio of R sub B cubed over R sub S cubed. That's R sub B over R sub S. Look, the ratio of cubes is the cube of the ratio. Okay, let's go there. Don't know what the temperature at the bottom of the lake is, guys. I'm trying to find that out. I do know that at the surface, it's 40 degrees Celsius. They used, I guess in this particular problem, or at least in the solutions I saw, they used 273.15 added on to 40. So 40 degrees Celsius plus 273, or plus 273.15, should be 313.15. Okay, makes sense to me. Looking pretty good, guys. Looking pretty good. T sub B at the end of the day, look at all this right here, guys. It's a bit of a mess, but not too bad. Could be a lot worse. These are all pretty important equations. Once you get there, it's a question of It's a question of where you're going to move with this thing. T sub b. T sub b equals all of that times this. So what is that? That's, well, let's go. Let's work with it. Can I ask a couple questions? Does P atmosphere go into P atmosphere one time? P atmosphere goes into here, whatever it is. Okay, so we got 1 plus rho g h over P atmosphere. Times rho b, or RB rather, over RS cubed times T sub s. Okay, now T sub s we already said is this guy. So T sub s they put the 1.5 in there too. The 273 plus 40 is 313, but it got 273.15 plus 40. They should, out of the context of what's going on, they should be telling you that. But that's big. That's it. I mean, I keep saying they're all important equations. I mean, they're all, I guess, equally important. One derives from the other, I guess you could say. If we plug in that's it. I mean, you plug in the appropriate stuff and you should be fine. Like I said, usually I don't like to erase any of this stuff, guys, but it's got to get erased. But you've seen what the procedures are. The procedures were clear about 10 or 15 minutes ago. At that point, when you saw that those procedures were clear, you just got to work the whole problem out. You've got the equation set up. There was, a number of these equations were already, where it was going to get to that was already clear quite a while ago. So let's put in some stuff here and figure out where we're at. T sub b is going to be, well, one's easy enough to look at, I guess, right? What's rho GH? The way they had, I'm trying to use what they use 9.81 and the whole thing. They use rho is 1,000, G is 9.81, in the Katz book at least, how they like to use it. H is the depth at which this is occurring. That's 2.5, 2.50, whatever. The pressure they want is 1.013 times 10 to the fifth. They just use 1.01. So it's a little bit confusing which way you're going to go with this stuff. I guess if you use 9.81 here and 9.8 right here, and you use something different right there, 1.013 times 10 to the fifth, it's not that far off, guys. I'll try to be really clear if I'm asking you the question on the exam. I do have to tell you one thing that's really, really important, and that is I know I just delivered the speech about absolute scales and how the pascals and atmospheres behave okay. They allow you to do proportions because there's a zero to which they both can go, a bona fide zero. We don't really have that. We don't have that in the Fahrenheit scale and in the Celsius scale. Yeah, I know there's the lowest place you can go, but it's not a zero. It doesn't lend itself to the mathematics of ratios. And the mathematics of ratios is immensely important in all of mathematics. Therefore, you might wonder, you just said they're both absolute scales, the Pascal and the atmosphere. Why are you not using the atmosphere? Because the Pascal is geared to the Newton per square meter. If I've got newtons, kilograms, meters cubed, meters squared, that kind of thing, the atmosphere doesn't work. I've got to transfer. If they give me atmospheres, I have to convert them. To pascals. If I'm comparing phenomena and we're consistent with the labeling of it, and there's an absolute zero scale, so to speak, everywhere present, you can use the atmosphere. But once they're asking for a specific answer, they can all answer specific answers, but you've got to use the 4. Once this is in here, this 1,000 kilograms per cubic meter, this 9.8 meters per second, this 2.5 meters, that's the MKS system of units. Pascal is MKS system of units. You can't use atmospheres. You can use it as a comparative phenomenon, absolutely, whereas you can't do that with Fahrenheit. You can't do that with Fahrenheit or Celsius regarding temperature. But for pressure, you can certainly do it as a comparative phenomenon, even if it was atmospheres, but you can't. If I got an MKS system going on here, I got to stay with the MKS system. So that's why it's there. This is 1 atmosphere. This is 1 atmosphere pressure in pascals, is what it is. Is it true that the radius at the bottom ain't that much? Here, the millimeters and the millimeters cubed and millimeters cubed, they all cancel out. 3.60 diameter divided by 2 millimeters and 4.00 divided by 2. This is a diameter divided by 2, you got radius. This is a diameter divided by 2, you got radius. And you're cubing it. And you're adding 313. You're multiplying 313.15 on all that. That's it. That'll bring it. That'll bring it. It's a mess. Didn't say it wasn't a mess, but it ain't bad either. I mean, like I said, about 10, 15, 20 minutes ago, you already saw what direction it was going to go. The only thing you had to do was grind it out and do it. Okay. So what do you have here? Well, it's what it is. There's enough to do here, but let's do this. Again, I'm sorry, these were millimeters. Yeah, and let me promptly dismiss them. You don't have to, that's not even an issue. Okay? When you do that, you're going to get an absolute temperature. Kind of like the lingua franca of temperatures is the absolute temperature. It's going to be 283.72 Kelvin. Really? Yeah. That's Kelvin. What is that in Celsius? Subtract 273.15. Subtract 273.15 and you get 10.57. Yeah, that's a lot colder than 40 degrees Celsius. 40 degrees Celsius is a very hot summer day. Down here is like a winter day almost, or quite cold. Here's your answer. And there is at the end of that, guys. Good problem for us. That's 53. Let's go to 81. We will, let me read that out, give you something to think about, I guess, on that, and I'll do some erasing here. 81, 2 glass bulbs of volumes 500 cubic centimeters. 2 glass bulbs of volumes 500 cubic centimeters and 200 cubic centimeters are connected by a narrow tube of negligible volume. The apparatus is filled with air and sealed. The initial pressure of the air is 1.0 times 10 to the 5th pascals. That's the initial pressure of the air that's in there. And the initial temperature is 17 degrees Celsius. The smaller bulb is immersed. Now watch out. The smaller bulb is immersed in a large amount of ice at 0 degrees Celsius. And the larger bulb is immersed in a large pot of boiling water at a temperature of 100 degrees Celsius for a long period of time. Determine the final pressure of air in the bulbs. Ignore any change in the volume of the glass. Model air as an ideal gas. This is amazing. It's a great question, guys. So there's 2 glass bulbs. One of them has 500, 2 glass bulbs. One of them is 500 cubic centimeters, 500 cubic centimeters for one of the glass bulbs, and the other one is 200 cubic centimeters. And The larger one is immersed in a pot of boiling water, the smaller one in ice, and they want you to find out what the pressure is after all that's done. So there's going to be two glass bulbs. The big one is 500 cubic centimeters, and the small one is 200 cubic centimeters. They're connected by a narrow tube. We're not going to worry about that. The initial pressure before anything's done is 1 times 10 to the 5th pascals, and the initial temperature, where you got 1.0 times 10 to the 5th pascals, that initial temperature is 17 degrees Celsius. Okay. 17 degrees Celsius is 290 degrees Kelvin. The smaller bulb is immersed in a large amount of ice at 0 degrees Celsius, and the larger bulb is immersed in a large pot of boiling water at a temperature of 100 degrees Celsius for a long period of time. Determine the final pressure of the gas in the bulbs. Ignore any change in the volume of the glass. This is a fascinating problem. We try to give, let's talk about it on various levels. I think the notes speak about it pretty well, I hope. And let's see what we got. All right, guys. There are initial circumstances, I guess you could say. And let me just quickly kind of look at it. Trying to find I think a way to do this, and perhaps it's not the only way to do this. Let me see what I can say here. Let's say that small l means large, small s means small, for our subscripts at least. The volume of the large bulb is 500 cubic centimeters. The volume of the small bulb is 200 cubic centimeters. Is there something to be said about that? Well, there's a lot to be said always, I think. I'm of that opinion, but the ratio of VL divided by VS is 500 divided by 200 is 5 over 2. VL is 5 halves S. VL is 2.5 times bigger. VL is 2.5 times bigger than VS. That means the number of particles that are present in the large bulb is 2.5 times more than what's in the small bulb. You understand 5 over 2 is 2.5. So if that's the case, so this is, I guess you could say one way to look at it. Initially, ladies and gentlemen, the pressure in the large is equal to the pressure in the small. The temperature in the large is equal to the temperature. That's not going to be the case after you put the large one in a container of boiling water. Or at least, well, we can argue that one too. But what's going to happen, you know, if they were separated, completely separated, sealed off, yeah, 100 degrees Celsius boiling water for one of them, 0 degrees Celsius of very cold water for the other, there's a big difference. Now, since they're connected, something's going to happen. But initially, here's what we got. Right. Is it true in the back of our minds, and we've seen this to the point we don't want to see this anymore, true. Yeah, that's definitely true. Okay. Do I want to explicitly go there? Maybe not. Maybe I want to just deal with n right now, not the p. If I want to solve for n, I mean, all that implies that capital N is PV absolutely. Look, let's just talk. They're telling us the pressure is 1 times 10 to the 5th pascals. We got to work with that because everybody's MKS system of units. There is 500 cubic centimeters and 200 cubic centimeters for a total of 700 cubic centimeters. A cubic centimeter is 1/millionth of a cubic meter. So it's 700 of those 1/millionths. You've got to make it. If they're giving you, there's a time you can't. If you're doing a comparison, you can get away with a lot of stuff. If they're insisting on the MKS system of units, which they are, oftentimes, and this is one of those times. Remember, 17 plus 273. 17 plus 273 is 290. That's that. All right, this is whatever it's going to be. 1 second, forgive me guys, I got to get some chalk here. .1749125. That's how many particles there are. What does that mean? Well, this is what it is, and this is what it's going to be, guys. I mean, you move it over, do the stuff to write it in scientific notation. I'm probably writing to too many decimal places, but let's assume they're perfect the way they did it. And this is the number of particles that are there. This is the number of particles that are there total. There's, what is that? Well, 2/5 of this number, 2 divided by 5, forgive me, no. 2/7 of this number. 2 divided by 7. 2 divided by 7 times this will tell you how many particles are in the small container. If it's 700, you know, there's 200 plus 500 is equal to 700. Divide by 700 on each side. 2/5 plus 5/7 divide by 7 is 1, the whole thing. 2/7, 2 divided by 7 times this is how many particles is in the 200 centimeters cubed container. 5/7 divided by this will tell you how many particles is in the 500 centimeters cubed container. Absolutely. How much total? Add the two, you got one, the whole thing. The whole thing is this. There's 2.5 times more particles. There is 2.5 times more particles in the large container as there is in the small container initially, when they have the same temperature. I think something crazy is going to happen, though. We're eventually going to be able to figure out the pressure and everything else. But once you have one of them, one of those containers very cold, and the other container very hot, the particles that have a very, very high kinetic energy are going to tend to want to migrate over to the other side. There's going to be less than 2.5 times more in the big container as compared to the small container. That ratio is going to change because the high energy particles, high kinetic energy particles associated with high temperature, I think they're going to tend to go over to the other side. We can still figure it out. All right, that's another story. At least you can argue it that way. We know you guys, and I already kind of delivered this speech. So N is the total, is NL plus NS. Okay, we know that. We know that. Note that in the short term, and for our purposes, no equilibrium temperature is reached because of the reservoirs constantly present. But nevertheless, there is an average KE and therefore an average temperature. It's the way I took it, the way they said it. Let's see what we got. Let's see what we can say. There's a lot to be said. Okay, you got the number up here. We know that. We're okay. We'll come back to it. Let me erase a few things, guys, and let's talk about it. Well, let's see. We just kind of, we said it, and of course, I erased it for us, which was great, right? Let's put that back up there. Let me just put this up here again. What's T equal to then? Forgive me, not T. What's N, number of particles? What's that equal to? N is going to be equal to, as a general format, PV over KB T. That's absolute value temperature. Okay, so we know that. That's pretty important stuff. We also know this. We also know, well, let me cut to the chase, guys. Maybe this will make a little bit of sense. Here's NL. Here's NS. Let's find out. There's going to be a pressure at the end. I don't know what that pressure is going to be. I'm going to call it P. The volume, well, that's the total volume of the whole thing. The total volume is 700 cubic centimeters. We'll see what that is. This is at the end. There's a pressure at the end in total. The volume is 700 cubic centimeters, which is 700 times 10 to the negative 6 cubic meters. KB is a constant. T is effectively a measure of the average kinetic energy. I don't know how to argue that if one of the things is in a boiling pot of water and the other one's in an ice pool. But there's got to be an average kinetic energy. There's got to be some kind of equilibrium if this is going on constantly after a long period of time. They've got to find a way to be somewhere, because they're not shutting off the fact that the water's boiling, and they're not shutting off the fact that it's a very large body of water that's at 0 degrees Celsius. 0 degrees Celsius for the small container, it's going to be put in a container 0 degrees Celsius for a long time, and the other one's going to be put in 100 degree. So small container is going to be put in water 0 degrees Celsius. Large container is going to be put in water at 100 degrees Celsius. And I guess there's an average, it's got to be an average temperature somewhere though. So there's some temperature associated with that. The volume of the 700 times 10 to the negative 6 cubic meters, that's the 700 cubic centimeters. There is some pressure, there's KB. What's the large one? There's a pressure in the large one when this is going on. There's a volume in the large one, which we know it's 500. This is KB, and there's a temperature in the large one. What's that going to be? Well, it's going to be pretty hot. There's a pressure in the small one. There is a volume, 200. Here's KB. Here's TS. I think this is where we got to go. At the end, there's a lot going on here, guys. So let's see what we want to say here on this. There's going to be a new pressure. I think it's going to be associated with this guy. I didn't write them in my notes like I should have, but I think I did later. Yeah, there I did. Yeah, there I did. Okay, so I should have written a lot of stuff. The P over here is going to be the P new. And the P new is the same as P sub n. P new. It's going to be PL at the end and PS at the end. They're all going to have the same pressure at the end. Why? It's one container. It's one big container. I don't know. It's not very obvious what it's going to be, but it is one big container. Okay, sure. Let's see what we got. Let me go back here. This was, wait a minute, wait, hold the phone. I shouldn't have said what I said. There's a reason I didn't have it in my notes, and I was complaining that I didn't have it in my notes, so don't buy this. These are the initial circumstances. This is the 1 times 10 to the 5th. This is 700 times 10 to the negative 6 cubic meters. This is KB, and this is 290 Kelvin. Is what it is. This is going to be a temperature, most likely 100 degrees Celsius, so 100 plus 273, that's going to be 373. This is going to be 0 plus 273, which is just 273. KB is what it is. VL is the 500 times 10 to the negative 6. VS is the 200 times 10 to the negative 6. There's a pressure here and a pressure there. The PL and the PS are definitely going to be equal to each other. Why? Because at the end of the day, guys, it's still one container. I'm already telling you particles are going to migrate over to the other side. The ones that are in the hot area are going to have more chance to find themselves predominantly over in the cold place. And the ones that are cold, I have less chance to find themselves over where it's a hot place. They're not moving that violently as the ones at 100 degrees Celsius are. So it's going to change. It ain't going to be 2.5 times more particles inside the large container compared to the small container after this is going on. It's going to be a smaller ratio. It's not going to be 2.5 times more particles contained in the large container as there are in the small container, surprisingly enough. At least that's what, on average, it comes out that way. However, after everybody reaches equilibrium, The volumes are what they are. 500 cubic centimeters. 200 cubic centimeters. I got to convert that to cubic meters. I get that. This is 700 cubic centimeters. This is 1 times 10 to the 5th. See what we got here, guys. I want to just see exactly what we're doing here. Right. Exactly, right. So what happens is, this is the initial status. Initial status is 17 degrees Celsius. That is 290 degrees Kelvin. This is case of B. This is 700 cubic centimeters, which is 700 times 10 to the negative 6 cubic meters. This is 1 times 10 to the 5th, 100,000 pascals. That's the initial situation. The ideal gas law allows us to speak that way. Period. With everything there. Now that everybody's gotten changed, this guy's at 100 plus 273, 373 Kelvin. Case of B is what it is. That's 500 cubic centimeters. This is whatever it is. And this is whatever it is. V sub S is 200 cubic centimeters, which is 200 times 10 to the negative 6 cubic meters. This is case of B. This is T sub S. This is 0 plus 273. This is 273 Kelvin. This is 373 Kelvin. Case of B's are what they are. The 200, the 500, you remember the business here. PL and PS are the same. They are the same because at equilibrium, since everybody is free to migrate, the pressures will equalize. And PL will equal PS, will be equal to P sub nu, which is P sub n. P sub n will be what these guys are equal to. So if that's the case, ladies and gentlemen, and it is, it's the most important problem, guys, the most important part of the problem. It's right there. Well, what do you want to do? Well, I'll tell you what. What do you say you multiply by KB on each side? Multiply by KB all the way across. Multiply by KB on each side. That's out of there. And then you got PV over T equals, now remember, I just said at equilibrium, PL is going to equal PS, is going to be the new pressure. That is huge. I mean, that cannot be overemphasized, I guess you could say. That's the key to the thing, you guys. That's the key. That's the key. So PL is P new, is the new one at the end of all that. This is V sub L. Multiplied by, this is T sub L plus Pn Vs over T sub S. True. True. May I say something? Can I take P, pull it out from the ratio V over T? Can I take Pn and pull it completely out from both of these? Wow, that's huge. That's huge. Pretty important stuff. I mean, once you get to there, that's pretty important. If this is the case, so much going on there, guys. This is the big thing. This is proportional to the number of particles present. This is hugely important. Let's talk. Just see if I can be seen on the screen here. Okay. Let's talk. This all came about. You can't we're not able to forget this, guys. I mean, all this stuff, these pertain to particles. These pertain to particles. A number of particles. PV over KBT. You got rid of the KB, but the proportions are still there. If P times V over T, if P times the ratio V over T is a big number, there's a lot of particles. If P times the ratio of V over T is a small number, there's not a lot of particles. Period. Is that believable? It is to me. Here's why. If there is a huge pressure and a huge volume, let's get a big answer on purpose here. Let's say there is, just forget about everything else. Just take a snapshot just of this guy, of what's going on right here. Later on, we'll throw them with this guy because they are equal, so I'm obviously going to get thrown. But forget it for now. Just deal with this. None of this problem exists, just this right here. You got rid of the KB. Let's get a huge pressure. Let's say we have a huge pressure in a container, and it's a huge container on top of all that, and there's not a lot of absolute temperature. How on earth are you going to have a huge pressure inside of a huge volume where particles have to move a very long distance to make the strike against the wall, to make the strike against the container? There's a huge volume. It's hard to have if you want to pressurize something, you usually compress it. Let's say the volume's huge and you still have a huge pressure. If you have a huge volume and there's still a huge pressure, there's a huge pressure, there's a huge volume with that huge pressure, huge volume, and you're doing it without a lot of kinetic energy. Huge times huge is really huge, divided by small is really, really huge. There's a lot of particles in the container that can do that. Only if there's a lot of particles in the container will that happen. The only way you're going to have a huge pressure, if there's a big, big volume and you don't have a big temperature, if you don't have a big absolute temperature and you don't have a big absolute temperature and there's a huge volume that has to be traversed by these particles that don't have a lot of kinetic energy because there's not a lot of temperature. Not a lot of kinetic energy because there's not a lot of temperature. Low temperature, huge volume to traverse, and you still have a lot of pressure? How on earth could that happen? Only with a lot of particles. A huge amount of particles. This is all directly proportional to the amount of particles. For a given, now, okay, good. We can stay here or go there, doesn't matter. For a given pressure, for some pressure, if you increase the volume and keep the temperature the same, you're going to lose. You've got to put more particles in there. If you're going to keep that pressure equal, you're going to keep the pressure the same. If you cut the absolute temperature in half, wow, that's half the kinetic energy. You're going to have to put double the molecules in there. If you ended up cutting the absolute value temperature in half for the same volume, you'd have to put twice the number of particles in there for the pressure to remain unchanged. If you cut this thing in half and you put 4 times the particles, you'll have double the pressure because the particles overwhelm the whole situation. But double the particles and half the temperature, 2 divided by 2, 1 stays the same. This plays a big role. Volume and temperature play a big role. If for a given pressure to occur, for a given pressure, forgive me, having said that, volume and temperature play a big role as far as how many particles you need for the pressure to happen in a particular way. What do I mean? If you were to make the volume 10 times more, if you were to make the volume 10 times the volume that it originally was, if you made the volume 10 times the volume that it originally was, with the same number of particles, the pressure is 1/10 of what it was. You have to make the temperature, if you made the volume 10 times as voluminous as it originally was, if you make the volume 10 times the size that it originally was, you have to make the absolute value temperature 10 times what it originally was to keep the same pressure. Otherwise, if you leave the temperature the same and you make the volume 10 times what it was, if you make it 10 times the size of what it was, you're going to have 1/10 the pressure. If you make the volume 1/10 of what it was and make the temperature 1/10 of what it was, 1/10 and 1/10 cancel. You still got the same pressure, believe it or not. Doesn't sound right. You got less energy. Yeah, I know you got less energy, but you're covering less ground too. You're covering 1/10 as much volume. So it works out. Yeah, you got the same pressure, but you're not covering the same volume. Hugely, hugely important how this plays out. The number of particles is directly proportional to this ratio for a given pressure. For a given pressure, V over T. I mean, we started here. The number of particles is directly proportional to all this. If you have a given pressure, and that's a constant anyway, so if P and KB are constants, V over T calls the shots. If you somehow made the volume 10 times the size that it was before, and then on top of that, you made the absolute value temperature 1/10 of what it was, 10 divided by 1/10 is 100. You need 100 times more particles. You need 100 times more particles than you had for the pressure to stay the same. Really? What if I don't have it? Then it's 1/100th of what it was. If you make the volume 10 times more voluminous than it was originally, if you make the volume 10 times the volume that it was, if you make the volume 10 times what it was, forgive me guys, I want to make sure this thing works. I've been talking for a while. If you made the volume 10 times the volume that it was originally, and at the same time took the temperature and made it 1/10 of what it was originally, 10 times big, 10 times the size here, 1/10 the size there, 10 divided by 1/10 is 100. You have to have 100 times more particles than you had before if you're going to keep that pressure. Period. If you don't, if you leave it alone, the pressure is dropped 100-fold. And again, play with the mathematics. Look at this stuff. It's pretty profound. And here they box off. They box off here and here. So it's already saying that. We're already kind of looking at what are we doing? We're setting up the particles here. This has all got to add up. The conclusions are going to be pretty interesting though. So let's see. Let's see where it goes. Okay, we got that there. Let me leave that there. This there, again, I don't like to erase any of this stuff, to be honest with you, but we did what we did. From here, from all of this, we went to that. Okay. All right, we know what it is. Let me erase a lot. Probably more than I should, more than I want to. But let's take this thing. Let's take this thing to the end of it. Okay. So with this being said, where is this going? Well, I mean, why don't we find the new, I mean, they want at the end of the day, they wanted us to find the new pressure. And that means finding this guy. Finding this guy, Pn. Well, to find this guy, Pn, just divide by this factor on each side. So what happens is you get they want to find Pn, so just divide by the factor that's on each side there. Okay. What do we got? Well, the top is going to be PV over T, like that. Let's get a common denominator here and see if we can tinker with this at all. Multiply this ratio by TS over TS. Multiply this ratio by TL over TL and add them. Yeah, that'll tell me a lot. Let's plug in all the numbers, I guess you could say. I've got this in the notes. Let's just what the heck? Let me just do it anyway. I think it's important. I think we should just do it anyway. P is 1 times 10 to the 5th. 1 times 10 to the 5th is 100,000. V, now here we go. Here we go. I'm going to be able to get away with what I'm about to do. I know it's 700 times 10 to the negative 6, 500 times 10 to the negative 6, 200 times 10 to the negative 6. The volumes of the entire, the large, and the small containers respectively. I get that. Because times 10 to the negative 6 will be here, times 10 to the negative 6 will be here, and times 10 to the negative 6 will be here, the 10 to the negative 6 will cancel. So that's true. 700 times 10 to the negative 6. I'm almost tempted. I'm going to do it anyway. I didn't do it in my notes, but I'll do it here. If it's a ratio that's going to block everybody out, it don't matter if you make up your own units, as long as you're consistent. As long as you're consistent. You got this over 290. I'll show you in a second. Let's just kind of see what we're talking about. All right, let me see what I can say here. I'll tell you what. I'll put it right here. Times 10 to the negative 6. You'll see what I mean in a little bit. Yeah, this is I guess easier done than said sometimes, or sometimes easier said than done. It's hard to figure out which one's best. Okay, you can take a 10 to the negative 6 and a 10 to the negative 6, which is also here. You can take a 10 to the negative 6 and factor it out. You can also take a 10 to the negative 6 and factor it out over here. 10 to the negative 6 over 10 to the negative 6, they're all out of there. So that's where that comes from. So you could take those out of there, guys. I mean, so I don't know at what point one. So you could take 10 to the negative 6, 10 to the negative 6, come right out here. That's 10 to the negative 6 right here, multiplied with all that. Take him out of here. That's 10 to the negative 6 times all of that. They cancel out. So vis-a-vis that, okay? Makes it easier to look at. I kind of jumped past that step, but it should be pretty obvious, I hope. When you actually grind that mess out, you will get, for 81, this is again, the problem we're still on, of course, Pn is 434.93 pascals. Pn is approximately equal to 1.2 times 10 to the 5th pascals. So the other one was 1.0 times 10 to the 5th pascals. 1.0 times 10 to the 5th pascals was the pressure of the whole system. 100,000 pascals, 1.0 times 10 to the 5th pascals was the pressure of the initial system at 290 degrees Kelvin, at 17 degrees Celsius. Here, with one of them at 0 degrees Celsius, one of the bulbs at 0 degrees Celsius, and the other bulb at 100 degrees Celsius, the pressure goes up. That's huge. That's it. That was the question they asked. That's the end of the story. That's the end of the question. I want to not end it right there. I want to say just a little bit more. For our looking at what's going on here. That's it. That's that one. And that's this one. I mean, obviously, this is the better answer is probably this one. I mean, don't write this on an exam, especially if it's a 2% error tolerance. Write this one. But that's still a bigger number. 116,434.93 pascals. About 116,434 pascals is more. The 116,000 something is more than the 100,000. 116,000 something is more than the 100,000. Which tells me that the average temperature, the average kinetic energy must be greater than the average kinetic energy associated with 17 degrees Celsius, with 290 degrees Kelvin. There's got to be a kinetic energy that's more than that if I'm getting that kind of pressure. T average, in a sense, is associated with that. So if you wanted to look at it, what would the T average be? Well, it said 290 is what I said. that ends it right there, guys. I mean, little mathematical So here's the extra, some extra on that, just to look at some of the what-if scenarios. The average kinetic energy's got to be more. Look, guys, I mean, at the end of the day, you saw how this played out, how we had to go to get it done, and how it all played. So we got that, and then we did a lot of stuff with that. We do know divide, solve for T. PV equals N KB. Yeah, you better believe it. And we knew what N was. We found it out early on. You didn't add any particles to the system, nor did you subtract any from the system. This T is going to be a T average. How are you going to do that? Well, I'll tell you what I'm going to do. The T average is going to be the pressure nu that you just discovered times the volume of everybody, the number of particles totally present, in KB. T average, here we go. 116,434, almost 116,435, which is more than 100,000. Already I'm being tipped off on this. Total is this. Assuming no other business goes on here, guys. Don't you remember we had that really long answer of 1.74915, 1.74915 times 10 to the 22. That's how many particles, everybody. This is K. Yeah, it looks about right. Yeah, it's a lot bigger than the other one was, or somewhat bigger at least. T average, 337.66. $337.66K. What was it initially? The initial was 17 degrees Celsius. The initial for everybody, everything there, was 17 degrees Celsius. That's 290, roughly. 17 degrees Celsius is 290 degrees Kelvin. 17 degrees Celsius is 290 degrees Kelvin. 290 degrees Kelvin compared to this is 47.66. Almost 48 degrees Kelvin more. What's 47.66? It's 47.66 more. 47.66 more. 47.66 more onto 17 is 64.66 degrees Kelvin. 64.66 degrees Kelvin. 64.66 degrees Kelvin compared to 17 degrees Kelvin. Yeah, it's got to, this, hey, look. I almost don't want to write down the initial. This is the initial they gave us. The initial. Don't throw this into any one of the problems until we already had it thrown in there. The initial was 290. Yeah, everybody was at 17 degrees Celsius. If you're going to put the biggest container of the two, the 500 cubic centimeter container and you're going to put it in boiling water for a very long time at 100 degrees Celsius, 2/5 of the original particles got placed there. They ended up moving. They went other places eventually, but you'll see in a second. But if you got the biggest container at 100 degrees Celsius, I know the other one's at 0 degrees Celsius, but there's not as many in there. There's not as many in there. There's 2/5. I guess you could say 2/5. Yeah, there's 2/5 of the amount. There's less than half. Less than half the particles initially present in the 0 degrees environment that they were put in. The bulb was put in a 0 degree environment. There was whatever. There was, that's 2/7 of the particles. Yeah, 5/7 of the particles. 5 out of 7 particles were in the hot container initially when this was happening. The average kinetic energy for this to happen is associated with the absolute value temperature of 337.66 degrees Kelvin. The average temperature after all this associated with average kinetic energy. The average kinetic energy of the particles is associated or would be associated with an absolute value temperature of 337.66 Kelvin, as opposed to what it was initially, was 290 Kelvin. Okay? So, this is crazy. What does that mean? Well, we already said initially it was 2.5 times more. There were 2.5 times more particles. There was 2.5 times the particles in the big container, 2.5 times the particles in the big container as are in the small container initially. Is that going to hold up? This is associated with an average. The container would have to have this average temperature. Some container would have to have this average temperature for this kind of pressure to be going on. And for the other situation, this average temperature would have to be present for 100,000 pascals. But for 116,434.93 pascals, almost 120,000 pascals, you need an average kinetic energy which is more than the average kinetic energy that was present. How much more average kinetic energy would you need? You would need you would need a kinetic energy associated with this. If you took the 337.66 Kelvin, and this is where the absolute value temperature works so great, and compared it to 290, that is Ke nu average divided by Ke original. How many times does that go into there? And that would tell you. And that would tell you how much kinetic energy on average. It's got to be going on that way, guys. That's fascinating. The ratio of the pressures. That's crazy. 1.16, 434. Yeah, so roughly there. I mean, I guess I did a round off and everything else. The ratio of the two pressures, all other things equal, notice we did not change the number of particles in either scenario. Nor did we change the volume, total volume of the containers. The total volume was not changed in either scenario, nor were the number of particles changed in either scenario. The only thing that made it different, you did not change the volume, KB does not change, and you did not change N. If you don't change N, and if you don't change KB, well, KB is a constant, you don't change N, and you don't change V, pressure and temperature, all other things being held equal, not changing, if you don't change everything else, if the pressure is doubled, the average kinetic energy has been doubled. If the pressure's been cut in half, the average kinetic energy has been cut in half of the particles. If we're talking about the same number of particles in both scenarios and the same amount of volume in both scenarios, then it is the same as the pressure. The ratio is 116,434 point something, 116,434 point something divided by 100,000 is 1.16. That's crazy. That's equivalent to ratio of new pressure divided by old pressure, the original pressure. That's of interest. Okay. One last thing I think we already just got it. Yeah, the whole thing is basically, I just showed it kind of in another way. Let me kind of just show it in that other way we talked about, guys. Let's have a look. Yeah, they kind of look, there was like maybe a little other way you could kind of look at it. I don't think that's a big deal. It's not, I don't even think it's necessary at this point. I think we hit it okay, but what the heck, we're there. It shouldn't, we've made it this far. Let's talk about it. They kind of went the same path here. I think I didn't get a real good look at it. I'm just going to re-looking at it. You could kind of come to the same conclusion. Yeah, I think it's exactly the same. Exactly how I did it. I did something like this. I started here. And then we said, okay, we know that now this one, I think it's not because I'm saying it, but because the mathematics is beautiful, done by people long before I was around. It's a beautiful conclusion in its own right. So when you talk about, and this is how we played the game, I think throughout the entire problem. We added in the two places where it was. So we can say a couple things that way, and then we said there's a bunch of stuff you could have said, guys. And I don't, like I said, I'm kind of getting away from that a little bit. You could say this is the initial. The initial is the 100,000 pascals. This is the 700 times 10 to the negative 6 cubic meters. This is KB. This is 17 plus 230. This is 17 plus 273. The 290 we're talking about, right? That's this guy. That's N. That's N. That's N. They're the same. That's where you get it. That's N right here. N1 is the pressure at the end. We'll say that's the new pressure. I'm just going to call it P. Pressure at the end. Now forget everything. I mean, work with what I did in the past. If that's good for you, that's good for you. If you don't want to look at this right now, turn this off and just look at the earlier stuff I did. But I think this is just something to maybe expand our understanding a little bit. When you're looking at this, we said there's going to be an average temperature. There's going to be a temperature, T, which is like an average temperature somewhere, sometime. This is P right here. This is V2. This V1 was 500 cubic centimeters, which is 500 times 10 to the negative 6 cubic meters. This is 200 cubic centimeters, which is 200 times 10 to the negative 6 cubic meters. So 500 times 10 to the negative 6 cubic meters, which is 500 cubic centimeters. 200 times 10 to the 6. 200 times 10 to the negative 6 cubic meters, which is 200 cubic centimeters. The B is like, this is the new T. This is going to be T new. That's the new T. I'm just writing it like that. That's going to be the new. That's going to be the average I wrote earlier, where I got the 337.66. The 337.66 that we got. This is the initial. This is 290 Kelvin. This is going to be 337.66. 337.66. Initial pressure was this guy, the 100,000. This is P right here. And I guess we could have done this. You could have gone P. Now go look at all the right side stuff. Right? And let's take, I mean, there's a lot to take here. I mean, there's P, KBT. Yeah, that's common to both. KBT on the bottom on both. P is common here. This is V1, V2. True. Yeah, guys, V1 and V2, the 500 or whatever one is which, right? Big or small, whatever. The big one is 500 cubic centimeters. Small one is 200 cubic centimeters. This is 700 cubic centimeters, which is 700 times 10 to the negative 6 cubic meters, is equal to 500 times 10 to the negative 6 cubic meters plus 200 times 10 to the negative 6 cubic meters. That's VI. PI, VI over KB TI equals pressure VI. V1, V2 what's going on here? Multiply by KB on each side. Divide by VI on each side. Look, VI over KB and VI over KB, divide by KB over, multiply by KB over VI on each side. Multiply by KB over VI on each side. Yeah. Multiply by T on each side, divide by PI on each side. The average kinetic energy associated with which is associated absolutely with absolute value temperature, with absolute temperature is directly proportional to average kinetic energy. The ratio of this is why they use the absolute value temperature scale. You can't do this with 100 degrees Fahrenheit compared to 50 degrees Fahrenheit. I know 100 divided by 50 is 2 over 1. And I know Fahrenheit and Fahrenheit cancel out. Yeah, I get it. The kinetic energies aren't at a ratio of 2 to 1. You have to have an absolute value temperature scale to get that. The ratio of the absolute temperatures is equal to the ratio of the pressures. Which is equal to the ratio of the kinetic energies. We already said that. That we said. Let me let it alone. But it's true. It's true. If we're talking about, it's true in a huge range of things, but it is really, really true if the volume is constant and the amount of particles is constant between scenarios. Even if it's not, we're talking about average kinetic energy anyway. So it doesn't matter if one has 10 times the volume of the other. 10 times the... Yeah, a lot of things could be going on, actually. But let me not open too many cans here, guys. But if it's an average per particle, it can be in a wide range of circumstances anyway. But man, there's a lot you can draw if you're holding everybody constant. The amount of particles constant in both scenarios. I'm going to keep the same amount of particles in both scenarios. I'm going to keep the same volume in both scenarios. Wow. There's a lot you can open up here. Okay, you look at this, you got to here. What does that mean? That means that T is equal to now we had to get the pressure first, guys. I'm kind of putting the carriage in front of the horse on this one. The ratio of the pressures times Ti will give you T. At the end of the day, that's 337.66 Kelvin. Now you have to know the pressures though. And that's not out. I mean, you got to go back to find the pressures. But if you knew the pressures, this holds. This holds. Yeah, it holds. It holds. Let me. There's a lot to say here, guys. This is only true. I'm gonna have to digress just a little bit. Forgive me. If you were going to change n, you are changing a dynamic here, guys. If you were going to take and say pressure 2 divided by pressure 1 is equal to N2 kBT2. Okay, yeah. So I guess I spoke more correctly about a half hour ago than what I just did. There's something to be said here, but the pressure's not you can't just. I know the KB cancels, ladies and gentlemen, but this right here, T2 over T1 is equal to P2 over P1 only if N2 and N1 are equal. If they're not equal, that's a lot of other stuff going on. So, yeah, stay here. This is true, but only if N is constant. Only if volume is constant. Look at this. This is P2 over P1. This is T2 over T1. I agree 100%. They are true. This is, put 2's and 1's, doesn't matter. T2 over T1 equals T2 over T1 equals P2 over P1. True if N2 and N1 are equal. Otherwise, there's other stuff that comes into it. So this is based on what we know. This is always the case if you can find the temperatures. If you somehow find the temperatures, guys, once you've got the temperatures, that's true. Okay, forgive me, guys. I just erased what I did not want to erase, but T equals TI, P over PI, absolutely true. But the volumes have to be equal, and the number of particles have to be equal. Because you got PV equals nRT, and you gotta, to do that, again, the number of particles gotta be there. There's a whole lot that's gotta go on for this to happen. And what we had said was PV, yeah, the volumes were equal, so they canceled. Remember, I had the V's right here. I can't remember where I erased, guys. I mean, I erased a whole bunch of stuff, but yeah, absolutely. You had P2V2 over P1V1 equals, you could even go with the, whatever, here, N1, N2, KB, T2, T1. These guys are out of there. You got the same number of particles, but even this complicates things. The V will complicate things. If the V's are equal and the N's are equal, then you got the ratio of pressures is you got to have equal numbers of particles in both scenarios and equal volumes in both scenarios. Then this is true. Regardless of whether or not, now that's true, period. That's the end of the story. That also equals ratio of kinetic energies. Even if the pressures don't, even if there's other issues coming into play, you guys, that I don't want to explore right now, this, on average, per particle, not total kinetic energy, guys. I don't want the total kinetic energy of the system or adding up all the kinetic energies to get the total internal energy of the system. I'm not talking about that. Regardless of what happens, if you can compare temperatures, absolute value temperatures, you can compare average kinetic energies. No problem. You don't need equal volumes. You don't need equal volumes. You don't need equal numbers of particles. However, to get to here, you need equal volumes and equal numbers of particles. Equal volumes and equal number of particles to make it happen. So there's a lot there. It's in that beautiful equation associated with the ideal gas law. PV equals nRT, PV equals capital N, K sub B, T. T is everywhere, and it's associated with absolute temperature, okay? I think that is it. There was actually there's a little more, guys, if you don't mind. Let me there's one kind of last thing I wanted to say on this, how this would play out. We look at it, and remember I told you it sure looks like there's going to be more of a tendency for more matter to find itself going to a place where it's low energy. It'd rather be in a low energy place. In all those collisions that are taking place and all the stuff that it's doing, all those energetic molecules have more of a chance to get over to a low energy place. So there's a lot. There's a good amount you could say on that. I just think it's. I think it's something that's worth saying in that regard. Let me Let me erase this, and then let me go. Let me just show you, again, originally there were 2.5 times the number of molecules in the volume that was 2.5 times the size as the small one. In the large volume, there were 2.5 times more molecules originally than there were in the small volume. The large volume had 2.5 times the molecules that the small volume had. And that was directly proportional to the volumes. One was 500 cubic centimeters, and the other one was 200 cubic centimeters. 500 cubic centimeters divided by 200 cubic centimeters is 2.5. There were 2.5 times the particles in the large volume as there were in the small volume at that equilibrium temperature of 17 degrees Celsius, 290 degrees Kelvin. When the large container was in 100 degrees Celsius, immersed in 100 degrees Celsius of boiling water, and the large container was immersed in 100 degrees Celsius temperature of boiling water, and the small one was immersed in a temperature of cold water at 0 degrees Celsius. That was immersed. That was the small one. I'd like to kind of demonstrate, hypothetically, at least mathematically, where this is going in that regard. Let's see what I can say here, guys. All right, guys. We're going to play on the. I'll try to go relatively quickly here, and play. Play some math games here and say, well, mathematically, this could be argued, is how it's going to play out. Okay, pull out one more of these here. All right, we said a lot, came to some conclusions. See what we can say here, guys. All right, so this is, let's give ourselves the maximum room, I guess you could say. All right, guys, this is problem 81 that we're about to finish. Now, we finished problem 81 quite a while ago, actually. I'm just kind of putting some more stuff onto it that I think helps in our thermodynamic discussion pertaining to this stuff. In this hypothetical, T average, the 337.66 Kelvin, we'll call it equal to T. Right now, we'll just say it's equal to T. We see, you guys, in this right here, in this hypothetical average, and we talk about the T average, the T here, we see that N sub L over N sub S is not. Let's say that's N2. There's one that's in the large container. N2 is the large container. N1 is the small container. I know I said that's true. It was true when it was 290 degrees Kelvin, and you weren't putting things in boiling water and you weren't putting things in ice water. The large one was going into boiling water. The small one was going into ice water, and this ratio held, and to help me solve the problem is what it did. We solved it a while ago, yeah. Now, however, When you reach that place there, V2, it's not going to be equal to V2 over V1. Observe. N2 is the volume. N2 is the amount of particles in the big container. N1 is the amount of particles in the small container. P is the pressure in both. This guy's V2. Now remember, PV2 KB T2. What's T2? That's 100 degrees Celsius, 373 Kelvin. What's the other one? That's 0 degrees Celsius, 273. So this is the P. That's 373 Kelvin. This is 273 Kelvin, the T1. Here we go. The P's are going to cancel, the KB's are going to cancel. It's going to be the P over K, basically this. The P over KB, P over KB, P over KB. P over KB divided by P over KB, they cancel out. You got V2 over T2. Divided by V1 over T1. Wow, it ain't volumes. In the past, you guys, it was V2 divided by in the past, it was V2 divided by V1. What do you mean? I mean 500 cubic centimeters divided by 200 cubic centimeters is 2.5. 2.5 times as many particles in the large container as are in the small container. Absolutely true. On average, absolutely true. That was the way it was. It was like that. It was in the beginning, we were doing this problem, it was this. And that's how we got through it. Absolutely. It was that way in the beginning. I am absolutely sure I spelled that wrong. Okay, so let's see. The beginning. Later, it ain't working. Later, it's not working. Later, it's not working. Now it's a different dynamic. Large, let's call this guy, 2 is bigger than 1. Let's say large divided by small. 2 is bigger than 1, large divided by 1. Large amount, small amount. Large amount and the big one. Yeah, but it ain't this. It ain't V2 divided by V1. This guy gets thrown in as a wrench. That gets thrown in there, messing everybody up. Ladies and gentlemen, if T1 and T2 are equal to each other, if T1 and T2 are equal to each other, it cancels out and it comes to this. The way we had it in the beginning. They were equal to each other in the beginning. 17 degrees Celsius. 17 degrees Celsius is 290 degrees Kelvin. 17 degrees Celsius in both bulbs. 17 degrees Celsius in both bulbs, that's 290 degrees Celsius in both bulbs. If T1 and T2 are equal to each other, true, but they're not. The hot one is hot, the cold one is cold. The hot one is 100 degrees Celsius, 373 Kelvin. The cold one is 0 degrees Celsius, 273 Kelvin. Absolutely. So there you are. That's how it works. Well, that tells you a lot. That tells you a lot. That tells you an awful lot. What does it mean? I don't know. I wrote it differently in my notes. I think we're better off we just knock it out. The big one is what? 500 divided by 373. Okay. already this 373 is going to make them smaller by it's going to make this guy smaller by a factor larger than the factor than this guy gets made smaller, this 273. You already see that this is not going to be as big a numbers. If this was 270, if the bottom was 273 and the bottom was 273, it's 500 divided by 200, 5 halves, 2.5. 2.5 times the particles, 2.5 times the particles there than in the other one, but not here. When you do that, you get the ratio is 1.83. The big guy lost people. That's not equal to 500 over 200. Why is that? Because this right here is not equal to V2 over V1. It would be if it would definitely be equal. I mean, this right here, if you actually do this, it flips up the whole thing with the whole, you get V2 over V1, this guy, okay. V2 over V1, the T1 flips up. Ladies and gentlemen, if these are equal, then you got V2 over V1, you got V2 over V1. Yeah, if they're equal. It's not the case though. If T1 and T2 are equal, if absolute value temperature T1 and absolute value temperature T2 are equal, they cancel to 1. You got V2 over V1 equals V2 over V. I agree, but not here. I talk about that. So what is it? It's just what I said. I mean, this is the ratio. Period. If the temperature is hot, you lose people. If it's cold, you tend to gain people from the warm, is what it's trying to say. You gain items. You lose items if it's hot. They tend to go somewhere. They have more of a tendency to go somewhere. Their pressure is going to be too big. They're going to overpressure the other ones. What's going to happen? Well, they're going to go there and they're going to equalize the pressure. For that to happen, they have to leave. There's got to be less than 2.5 times the amount in the large container as was in the small container if there's going to be that kind of migration from the large, which is being boiled, which is dealing with boiling temperatures. That's it. This is what's the whole thing's about on that. These. How do those go? I mean, when you actually knock this out, you get this. This division, this divided by that is that. That's all it is for this hypothetical averaging. The ratio of the guy in container 2, the big container, of particles, the ratio of particles in the containers, the number of particles in container 2, the big container, in this case 500 cubic centimeters of container, that's the number of particles in the 500 cubic centimeter container. 500 cubic centimeter container, how many are present when all this stuff's going on, the boiling and the cold and all that stuff? Well, you got this many in the big container. You got this many in the small container, and the average ain't going to be 2.5, it's going to be 1.8. Remember, what did we say? Well, 1.83, something like that. Why is that? Because it's not just the ratio of this. If there's some kind of disparity like that, you're going to get, on average, how much of this is they'll reach an equilibrium temperature between the two. They didn't really go. There's a lot that was not said here. There's a lot that they did not tell us. But this is mathematically valid. If not in the practical sense, it's a little different dynamic. Once they do reach the place where they're supposed to be, if you could somehow get an average temperature, if one is always going to be 0 degrees Celsius, one is always going to be 100 degrees Celsius, there's going to be that equilibrium temperature. And we found it. We found it. It was going to be, as we said, what was it going to be? It was going to be the 337, so what is that, 27 and that's 64.66, right? When we do it, let me try to do that. Let me figure it out. Yes, that is 64.66 Kelvin. 64.66 Celsius. 64.66 degrees Celsius. Wow, that's a lot more than 17 degrees Celsius. I guess that's why the pressure's more. And that would be the equilibrium on it. That's how it goes. They didn't ask us any of this stuff, but there's some fascinating logic associated with what we're talking about, guys. And like I said, when I did the lecture on thermodynamics, I was telling you guys, I think within the context of problems, it's going to work a lot better for us. All right, I want to thank everyone for your patience going through this, and all the best to everyone. Take care.